Hi, my name is Andrea López, and I'm going to talk about Gaussian mixture square root filters for cislunar angles-only relative orbit estimation, which is a pretty long title, but hopefully by the end of the presentation, we know what we're talking about. Um, so we are in a cislunar environment. There's an increased interest in the last few years on this particular environment, and we want to do relative orbit estimation because it would be a good capability to have without ground intervention to be able to estimate the orbit and track an object that is somewhere around our spacecraft. And we're using angles only, which, any optical sensor can produce this type of measurements, and many spacecraft have cameras on board, and it is inexpensive and not power hungry. But we know that with angles only, what we obtain is a line of sight measurement. So we don't have an idea of the distance to the target, of the depth of that line of sight vector. And we also know that when we have a linear description of the relative orbit, this estimation problem is not fully observable. But when we add nonlinearities to the problem, on those higher order effects, we can pick up some trends that add to the information and that make the problem a little bit more observable. So cislunar space, three-body problem, lots of nonlinearities, so it seems like a good candidate to apply this type of estimation here. So for our estimation problem, we have the CR3BP for the dynamics and the angles only for the measurements. We do not have a mismatch between the generation of the synthetic data and the filter, so we are using these models for both. And we have two different relative orbit scenarios. We're going to focus around the 9-2 NRHO that is proposed for the gateway. And in scenario number one, we have a lead follower configuration where the target is 1 hour ahead of our observer spacecraft. And in the scenario number two, what we have is our observer in the same NRHO orbit, but we have the target on a synchronous quasi-periodic orbit, which means that it's orbiting somewhere around the NRHO and it doesn't have a secular drift. So to get a better idea of what is going on with these orbits, I have these animations, and you can see how the lead follower configuration has a repeated trajectory across multiple orbits. And then the QPO is, QPO2 and RHO is a little bit more messy, a little bit more complicated to describe. So for our filtering approaches, we're focusing here on a square root unscented Kalman filter and a Gaussian mixture version of this filter. So for the square root UKF, we have here pretty much the typical diagram, the same as for the UKF. The advantages of using the square root version is that we have an increased numerical stability, and we also have a guarantee of positive definiteness in our covariances. And another advantage, for example, is that when we are generating our sigma points in the UKF, in the standard UKF, we have here a generation of sigma points and another one here. We have to calculate the Cholesky factor every time we want to do that. So in here, that Cholesky factor is readily available because it's what we're using in our filter. So that's one step that we can omit. Now for the Gaussian mixture version, we wanted to do like the dumbest, the simplest implementation of this Gaussian mixture. And so we have here the diagram from the previous slide, and now we just have 5 of them. And the initial conditions are drawn from the same distribution. So each one of the filters is going to have a slightly different initial condition, and then we're updating the weights at each time step. But there is no merging, there is no pruning, there is no splitting of the mixins is just they are doing their own thing from the beginning to the end, and then the weights oscillate. This is just an illustration that to show that the resulting mixture is not necessarily Gaussian at all. This is, of course, a 1D representation. And so if you can now imagine this in 6D, that's actually the case that we're looking at. So now let's go with the results. As a baseline, I have here a comparison for different filters. And for the baseline case, we define the prior covariance as a sigma of 10 kilometers in position and 10 meters per second in velocity. We have a measurement cadence of a measurement per minute. We have a measurement noise that is actually quite generous compared what we could get down to using this type of measurements. You can get down to like 10 to the minus 5. And for each one of the results that I'm showing, we ran 50 Monte Carlo runs. So in here, you can see in this image on the left is the RMS position error and the RMS velocity error, with the dashed lines being the 3 sigma bounds. And we can see how the EKF is diverging, and it's not really doing very well at representing our state. And for all the other filters that we have, they are performing pretty much compared, have pretty much the same, and it's more or less what we would expect for the baseline case. So now that we know that things are working out in the baseline case, we will try to break these filters and see what happens when we make things more complicated for them. So the first subcase for this is applying a factor to the initial covariance to increase it. And then for this case, we have some initial conditions that are biased and some that are unbiased. Second subcase is applying a probability of a measurement being unavailable of either 25, 75, or 25, 50, 75, or 90%. And then those two prior cases are with the lead follower configuration. And then we're also looking at how this relative orbit geometry can influence in the case with the NRHO to QPO relative motion. So for the varying knowledge of initial conditions, these plots have a lot of information. So in here, you can see how the dark colors are for the biased cases and the light colors are for the unbiased cases. And then we have the solid bars being for the single filter case and the dashed or the diagonal strokes lines being for the Gaussian mixture case. And what we're looking at here in the x-axis is the percentage of time that each one of the runs has the error being greater than the 3 sigma bounds. So it's kind of a measure of consistency of the filter. So I also have to say for the last bin, that is 50 to 100%, while the other bins only have like a 10% of that time. So it's a different size bin. And we have, again, 50 runs. So what we would want to see is all of the runs being in the 0 to 10% case. But what we see here, for example, for the green case is that all of those cases are failing or not being consistent. But that corresponds to 1,000 kilometers and 1,000 meters per second. So like the initial covariance given to those filters is quite large. So yeah, those cases are not really working. Let's forget about those. Let's focus on the rest. So for the blue and orange cases, we can see in the blue how most of the cases, or like a high percentage of the cases, are in the 0 to 10% bin, which is what we would want to see. And we also see how the Gaussian mixture version of the filter is performing a little bit better than the single filter, which is great. And we can also see that with the orange here, we have the solid lines being larger here than the dashed lines, which also says that the Gaussian mixture is performing a little bit better in terms of consistency here. In the intermediate case, this orange case, we have quite a wide distribution of the Gaussian mixture results. So looking a little bit more deeper into this, looking at the post-fit residuals, here for the without bias case and with a bias case, we can see, again, forget about the green, and we can see in the orange case how we are pretty much extracting all of the information that we can extract from um, the filters. In this case, in the bias case, there's a bit of a divergence around the first pass through the peridune, but then it converges again, and it's consistent with the distribution that we would expect from the post-fit measurement residuals after they have extracted all of the information. So now for impact of missing measurements, same type of plots. We see here how there's a bit of a degradation with the increased probability of missed measurements. And we can also see how the Gaussian mixture version is performing a little bit better than the single filter. And actually for the 25% loss and 50% loss, all of the cases are in the 0 to 10%, which is a great result. And then when we look at the last bin, we also see more failed cases for the single filter than for the Gaussian mixture. And now when we look at the RMS for this case, we can see how the level of error increases when we increase the percentage of missed measurements, which is what we would expect. However, the 3 sigma bounds are not increasing to that degree, which I think it's an interesting result here. Now, for the impact of the relative geometry, we have here the same type of plot again. We have the cases for the single filter, either are successful or do not do good at all. There's no in between, but for the Gaussian mixture cases, it's a little bit more nuanced. There are cases that fail for a little bit of our simulation period, and there are cases that, it is a range really. So when looking at the RMS, again, we can see how the level of error for both filters is in the same order of magnitude, but the 3 sigma bounds are not. So what that means is that the Gaussian mixture version is going to be a little bit more consistent throughout than the single filter that just has it either converges from the beginning or it doesn't. But we also see how our errors are very close to the 3 sigma bounds. So looking a little bit deeper into this, looking at one arbitrary run, we can see here the different colors are for the different mixins, and then the black is for the total mixture. And we can see how the blue mixin is performing better than the others, but yet our mixture mean is not super close to that mixin performance. So when we look at the post-fit measurement residuals, what we see here, or actually what we do not see really well, all of the colors that correspond to the different mixins are pretty much overlapping here. So if we really zoom in a couple of orders of magnitude, then we would see how they are not exactly the same. But for this level of noise and for these, for all intents and purposes of this filter, the filter cannot really distinguish in the residual signature between the different mixins. So this hints at some unresolved ambiguity, at some observability issues, which is an interesting result, and we'll have to investigate a little further into that. So for the conclusions, key takeaways are that We are going to need advanced filtering techniques in these complex scenarios. You cannot just throw an EKF at it and hope for the best. Angles only is really cool, but it's also very tricky because you don't get that much information out of a measurement. Um, Even the simplest implementation of a GM can improve our consistency and robustness across all of the cases that we looked at. And yet, some results hint at unresolved ambiguities or some observability issues. And this is something that I want to look a little deeper into in future work. For potential extensions, well, one of them is looking at different metrics for evaluating the performance or the consistency of these filters because the mean and covariance of a Gaussian mixture are not the most descriptive parameters to use. Another extension that I'm currently working on is analyzing the impact of adding observer uncertainty to our model. Right now, we're assuming we know the observer state perfectly, but as we add uncertainty to it, how does that affect both the dynamic update and the measurement update? And we're doing that with a considered covariance implementation. Then I also want to look at specifically at reducing the levels of noise that we're introducing into our simulation to see if in those cases we will be able to disambiguate the different mixins. And of course, I would like to add adaptive mix and pruning, merging, splitting, make the Gaussian mixture filter a little bit smarter. And with that, thank you very much. And if you have any questions, please feel free to email me at this email. Thank you.